As we start a new section here in 2.2, it's important to keep in mind the goal of all of Chapter 2. We mentioned this in the last set of videos, but the goal of Chapter 2 was to help us see how we might be able to take an integral and repurpose it to find more than just an area under a curve. In the last section, we took a look at how we could use an integral to find areas between curves. However, in this section, we're going to take a look at how we can use an integral to help find volumes of some complicated solids. So to help try to understand the idea here and to see the connection to a Riemann sum, we're going to go ahead and take a look at the four pictures that I have below here. Notice that each of these pictures here in this kind of reddish pink is something that has a volume. It's some 3D figure. And I could imagine kind of adding up the volume of those figures by imagining taking little thin slices. Kind of like I have here in blue, where I kind of can see this is kind of like one of the slices of the figure kind of pulled out. Now some of these slices are kind of obtained from horizontal cuts, others are obtained from vertical cuts, like in this last picture. But either way, I could see that if I was able to find the volume of this blue slice, I could then kind of add up all the volumes for all the individual slices, and I could get a grand total volume. Now our goal is going to be to try to expand upon this idea to make slices that are easy to calculate the volume of, and that hopefully then will roughly approximate the volume of the overall figure. And then if we can improve our approximation, we might be able to approach the precise volume. So to help try to understand how this works, let's take a look at the picture that I have down below. So again, we're going to be going to a weird 3D solid, kind of like this blue picture here. I don't know, maybe this looks like a loaf of bread or something like that. And I want to go ahead and make cuts into this, so that way I can get some sort of a shape, some sort of a cross section that I can find a volume for. So let's imagine that we have a shape that looks like this. Okay, so you can see it's here on the kind of lined up above the x-axis. Maybe it starts next to some x-coordinate of a and stops at some x-coordinate of b. At least that's kind of what it falls in between. And I'm going to imagine making cuts into this loaf of bread, if you will, by doing these kind of vertical cuts that I have here. You can maybe imagine that like this little square here is like a really sharp knife or a blade or something like that, and I can slice into it. And when I do that, I can see that there's going to be some sort of a pink space that would be left. Like if I was to break this loaf of bread in half and just stare at one end of it, I could imagine seeing this pink stuff. And our goal then is to say, how can I use that cross-section to try to go ahead and estimate the overall volume of this very awkward figure? Well, what we're going to imagine doing is, as usual, taking our interval from A over to B and dividing it up into a bunch of smaller sub-intervals. And once I have these intervals, I'll do something like the following. Take a look at the second picture here. You'll see here that I have one interval established, and it goes from a point xi minus 1 to a point xi. So just imagine I have a bunch of my x's numbered. And so if this is, I don't know, x number 8, then this is x number 7, the x that comes right before it. I'll choose a special x in there, which is where I'm going to imagine making this cut into the figure. And that's where I get this sort of a pink outline that's happening here. Now what I'm going to do is I'm going to just imagine stretching that pink area that I have and giving it some thickness. We'll assume that that thickness again up here is delta x. And what I essentially get after doing this is I kind of get like a slice of bread out of the loaf, or at least something kind of close to a slice of bread. And you can see here that if I was to make a bunch of these different cuts and kind of put all of them next to each other, I have a bunch of these kind of awkward slices. And if I was able to find the volume of each one of these slices, again, we could add all of them together, and that wouldn't quite give me the volume of this original figure, since these slices are kind of jagged, if you will, or they kind of stair-step up, and they're not as smooth as the original picture. But at least it would give me a starting approximation. And then, as always in calculus, we might be able to expect how we could improve the approximation. What if I was to say, let's let the number of slices that I'm going to use approach an infinite number? How about instead of like 7 slices of bread like I have here, what if I use 7 million slices? They'd be a lot thinner, but I bet I could start to get this smoother sort of increase and decrease along this top edge of the loaf that I'm looking for. So this kind of leads us to the definition that we have in the box below. Let's suppose that this blue solid up here is called S, and we can already see it lies between a value of A and a value of B measured along the x-axis. Well, if the cross-sectional area, that is that pink area that I have there, the cross-sectional area of S in a specific plane, px, that is, I'm slicing here with this blade, px, and I'm going perpendicular to the x-axis. Let's suppose that that pink space is given by ax. Again, I'm going to see here that that pink area is totally dependent on where I make the cut. If I make my cut towards the middle, I'm going to get a big pink piece. But if I make my cut near the end, I'm going to get a very small pink area. But as long as that area is represented by a continuous function, then I could easily state that the volume of an individual slice could easily be given by just saying, take the area at that special x point, give it a little bit of thickness, and that creates that volume for an individual slice. I now would want to add up all of the slices that I have. I'll start at slice 1 and go to slice number n. And then to improve the approximation, we'll take a limit as n goes to infinity. So this here would represent the volume. Now, like we talked about in the last section, we should notice again that this looks unbelievably similar to the idea of a definite integral. Except now instead of having a function called f, we just have a different function a. But overall, this can still then be transformed into the definite integral that looks like this. And I should again be able to kind of see the same basic behavior and associations between the items within this integral that we had in the last section. Again, I'll notice that this a of x is representing that area of the cross-section, dx in some sort of way is representing that thickness, and a to b is kind of indicating where all my different slices are going to be occurring. They start at a and they go to b. So I could also imagine the same sort of thing if I maybe had a solid that was going to be positioned, bounded between two values on the y-axis. You could imagine what if I took this picture and I just kind of rotated it so the loaf was kind of positioned going up and down as opposed to going left and right. If I did instead go ahead and change it so I rotated the picture and kind of brought this end up this way so it was standing vertical, then I could do the exact same thing. I would just be making cuts horizontally into the figure, and I would have a dy question. So in the next video, we'll take a look at some examples of how we can start to put this to use when we can see that in certain cases we end up with some very easy cross-sections and some very easy formulas that we can come up with for the area of those pink slices.